Right, so we're going to do this packet that's provided by the College Board that is going to talk about the relationship between average values associated with motion, and also talk about some vocabulary of motion, indefinite integrals. So if you're keeping track of topics, we can call this topic 8.2. And you guys are going to do this card sorting activity dealing with the average values associated with motion. But before you do, I just want to remind you about some relationships. And that last paragraph talks about it some, but I want to talk about a little bit more. But the position function in this activity is going to be x of t. Now, position functions in other activities, it could be y of t if the particle is moving along the y-axis, or s of t also. The velocity function is almost always the same. Represented by v of t. But if we want to use the position function, the velocity is the derivative of the position function. And then the acceleration function is going to be a of t, which is the derivative of the velocity and the second derivative of the position function. Now, one thing we haven't talked about is you can also go the other direction. So we go from velocity to acceleration, but you also can go from acceleration to velocity. Right? So if we have the acceleration function and we want the velocity, we're going to integrate it. So the integral of a of t dt is going to give you the velocity function. All right, and we also can go up the ladder the other direction to go from velocity to position. So the integral of the velocity function is going to give you the position function. Okay, so that's a new relationship over there. Right now, this card activity is all about average stuff. And so one thing that you are looking at in the activity is the average rate of change. So let's remind ourselves what that is. This is the average rate of change of f from A to B. All right, so we really, for average rate of change, we're really just using the slope formula. Okay. Another average thing we've been talking about lately is the average value. All right, and so that's where we do f average is equal to 1 over b minus a of the integral of f of x dx. Sorry, let me try that again. A little short on space. Ugh. Okay. Now, one thing I want you guys to know is that these two things are not the same. The average rate of change and the average value are not the same. The average rate of change is the average rate at which the function is changing. The average value is over that interval. That's the average value of the function, not how much it's changing. So these are not the same. But let's talk about what is the same. All right, so we want to figure out what is the same as the average rate of change of f. That's going to be the average value of f prime. F prime is the rate of change. Now, just f prime total is the instantaneous rate of change, but if we use this average value formula, that's going to give us the average rate of change. So f average of 1 over b minus a, and then we do this integral. I didn't do from a to b. We should have done that. Of f prime of x dx. Okay. Now let's talk about these relationships, like average rate of change and stuff, with position and velocity and acceleration. Okay, so the average rate of change of position is equal to the average value of the derivative of position, or position prime, which is going to be velocity. All right. And then the average rate of change of velocity. So if we find the average rate of change of velocity, we're basically finding the average acceleration. All right, and that wherever average value of velocity, we could just say average velocity. That would probably make a little bit more sense. Okay. All right, now I'm going to scroll down to these cards. Mine is a little different than yours. My pages are just in a different order. It's no big deal. There's two of these that are a little weird. I just want you to understand what it means. All right, so right there on card 9, where we have that, that's just kind of a weird notation. So at the bottom, I'm going to write down what that means. So the numerator of card 9 means that it's someone took the integral from 2 to 5 of some function and got x of t, and then you are evaluating that from 2 to 5. All right, so that's what that symbol means. All right, then once you know that, you could probably guess what card 12 means right there, the numerator. All right, that means someone took the integral from 2 to 5 of some function and ended up with v of t, and you're evaluating it from 2 to 5. All right, now you don't have to figure out what that equals, you just have to figure out what that means. You have to figure out what those functions were. All right, so you guys pause the video and do that card activity, and then start the video back up, and we'll finish up the packet. Okay, So we're going to be understanding the vocabulary of motion and definite integrals. So we're going to start off and just kind of fill in these blanks using that word bank. So to find the new position of a particle moving along the x-axis, what we're going to do is add the starting position and to the integral of the velocity. Okay, and we've done this before. I just want to show you what it looked like before. So we want a new position, so we'll call it x of b. All right, that's going to be equal to the starting position, which we'll call x of a, plus the integral from a to b of the velocity, or the derivative of the position function. So in the place of there, we also could have v of t. All right. Then for number 2, to find the total distance traveled, you integrate the speed. And if you guys remember, the speed is the absolute value of the velocity. All right, so that's the total distance traveled. That's going to be equal to the integral from a to b of the absolute value of v of t dt. All right. And then to find the change in position, you're going to integrate the velocity over the time interval. And this is also called displacement. So this is different. It's not the total distance traveled. It's just the change in position from starting to the end time. All right. So displacement is equal to the integral from a to b of just the velocity. Okay, so we're going to use those 3 ideas to answer several questions. So we're going to start with part 2. So the particle moves along the x-axis so that at time t, its position is given by x of t and velocity is given by v of t. At time t equals 2, this is important, the particle is located at x equals 5. The following graph gives the velocity of the particle over the time from t equals 2 to 7. We're going to match the numerical expressions to their verbal statements. Now, one thing I wish was on here is that the horizontal axis is t and the vertical axis is v of t. It tells you that in the words, it just doesn't have it on there. And I hope you guys remember that when you need to integrate graphically, this is where you add or subtract the areas. So integrating graphically is adding and subtracting areas. All right, so let's just go ahead and find the areas of those 2 rectangles. So we have a base of 3 and a height of 2, so 1/2 base times height is 3. Base of 2, height of 2, 1/2 base times height is 2. Now, if we were just straight up integrating, we would subtract if it's below the x-axis, add if it's above the x-axis. All right, so One asks us the total distance traveled by the particle over the interval from 2 to 7. So that's basically integrating it, but with the absolute value. So in that case, we wouldn't actually subtract the 2. We would do the absolute value. We would add it. So that's going to match up with A. All right, the position of the particle at time t equals 7. That's where we're going to use this number 1, where we do the starting position plus our integral of the velocity. So the starting position at time 2 was 5, so we'd start with 5, and then we would integrate it, and that's just straight integration where we add if it's above the x-axis, subtract if it's below. So that's going to be C. And then the change in position is just straight integration of the velocity function. So that's where if it's above the x-axis, you add, below the x-axis, you subtract. All right, let's look at another one. For part 3, the particle moves along the x-axis so that at time t, its position is given by x of t and the velocity is given by v of t. Match the following integral expressions to the verbal statements. So you guys try that on your own. All right, pause the video if you didn't have time. But total distance is going to be c, position is going to be a, and then the change in position is going to be b. All right, and then part 4. So this time, still the particle's moving on the x-axis. All that is the same. At time t equals 2, the particle is at -1. The following table gives the velocity of a particle selected times over that same interval we've been talking about. But this time, because we're using a table, if you want to integrate using a table, you have to use Riemann sums. So this one is going to be left Riemann sums. So let's just write a statement that integrating with tables or tabular integration, you have to use Riemann sums. All right, so the total distance traveled, that's the one where it's absolute value. So when it's total distance traveled, there shouldn't be any negatives anywhere in your problem. And that is choice B, because we did a Riemann sum where -4 technically was the left. Now the distance between those two is 3. Distance is absolute value, we use +4. The distance between those is 2, which is here. And then the left is 6, so that should be B. All right, and then for the position function, we have to use that -1. And then we do the Riemann sum, so the left would be -4, that distance is 3, and then left is 6, that distance is 2. So that matches up with A. All right, and then the last one, the change in position, is just straight Riemann sums with nothing changing, nothing added to it. That's going to be C. Okay. So in our own words, or in my words, we're going to talk about the distance between the position, the displacement, which is the change in position, and the total distance traveled. Now this is easy to get these things mixed up. So don't forget you have this information that you could pull back up sometime if you need it. But the position is the location of a particle on the number line. All right, the second part of this, we have to determine if this can be negative and why. So the position can definitely be negative. Since the location can be left of the origin. Okay, so that's position. So let's talk about displacement. The displacement is the difference between the ending and starting positions and this also can be negative if the ending is to the left of the starting. And then the last one is the total distance traveled. Is the sum of the distance left and distance to the right. So you're not really looking at direction, you're just looking at distances, and this cannot be negative. All right. So your assignment is to finish this packet. So you have a table to do and then just 3 problems to do at the end.